Hello, my name is Tumelo Matata, and this is our Fluid 2024 assignment. On my right, I have
Chayamba Malinga,
Catherine Woodley,
and on my left, I have
Jason Johnson,
and Sonelisi Rekibido.
And those are our group members. Thank you.
The above pipe flow problem aims to estimate the downstream pressure P2 where water flows through a pipe undergoing expansion. Our relevant theoretical assumptions would include an incompressible, steady state and inviscid flow in which losses are negligible. Correspondingly, we can assume an inertial reference frame and that the fluid is moving along a streamline. Due to these assumptions, the continuity and Bernoulli's equation are applicable. The continuity equation can be used to relate the velocity before and after pipe expansion. With the relevant velocities determined, Bernoulli's equation can be applied between 2 points just before and after pipe expansion. Some key considerations for the experimental setup are ensuring minimal friction to approximate the assumption of negligible losses, accurately control and measure flow rate to have a fixed V1 value so as to apply Bernoulli's equation, a reliable pressure gauge to precisely determine the pressure drop before and after pipe expansion.
Final solution included a bucket with a hole at the top to allow for water to flow in, as well as a hole at the bottom through which a pipe system was connected for water to flow out. Behind the bucket, a cardboard was placed with graph paper on it, as well as graduations on the left side of the bucket. Across the pipe system was a manometer on either side of the two connections with 2 static pressure ports. Additionally, a stand was placed to allow for horizontal flow of water through the pipe system. Additional to that, a mark was made while at rest and no fluid was flowing through it to ensure the initial conditions were taken account.
We're currently checking if the fluid in the manometer is leveled using a leveler on the device.
Our methodology is as follows. In order to account for the pipe expansion, a PVC pipe was attached to a polymer bucket with a greater diameter. PVC was chosen due to its smooth characteristics to minimize frictional losses. Thereafter, 2 small holes spaced 157 millimeters apart were cut onto the PVC to measure the upstream and downstream pressures along our manometer. The manometer was built with small malleable tubes which were crafted into an M shape. The M shape allows us to compare the pressures at 2 locations simultaneously without the water and oil mixing. The change in oil height corresponds to a pressure difference between the 2 points in the PVC pipe. This tube is filled with oil as it is less dense than water. This creates sensitivity that is enough to provide clear pressure measurements. The bucket is filled with water using a hose pipe to create a pressure that will push the water through the PVC pipe. The bucket acts as a reservoir, like the upstream section of the theoretical system. It is seen here that the pipe outlet is closed to build pressure in the system, simulating the starting P1 at the inlet before the water begins to flow. Once the pipe outlet is open, the flow through the PVC pipe creates a pressure difference which is then captured by the manometer. The difference in oil height in the manometer indicates this pressure difference.
Our experimental conditions include a fixed pressure head determined by the height of the water in the bucket and the maximum tap flow rate through the hose pipe. We measured the flow rate by timing how long it takes for water to fill the measuring cup and read pressure changes using the manometer with rigid grid paper to track fluid movement. We estimate an uncertainty of around plus minus 5% based on potential errors in timing with the stopwatch, reading pressure levels on the manometer, and volume measurements from the bucket. This estimate accounts for small inaccuracies in manual timing, reading fluid levels, and basic equipment calibration.
In order to obtain change in H in the manometer, the following equations were used: mass flow rate equation, hydrostatic pressure equation, continuity equation, and Bernoulli's equation. For the comparison of results for theoretical versus experimental, the errors for V2, P2, and change in H can be seen in the table above. Although the percentage error for pressure appears to be negligible, the effect of the inaccuracy can be seen in the calculated errors for V2 and change in H. This error can be accounted for due to the fact that Bernoulli's equation was utilized, and this equation assumes inviscid flow. However, under experimental conditions, the flow has friction between the fluid and the pipe walls and causes a loss of energy. For simulation versus experimental. Similarly, there is a large discrepancy between the simulated V2 values due to the assumptions made for the simulation. This includes an assumption of inviscid flow through the pipe system. The actual effect of the readings can be seen in the simulated height of the manometer. For simulation versus theoretical, there is also a discrepancy between the V2 value of theoretical and simulated values. This exists as a result of the simulated experiment having a bucket whose volume is non-constant, while the theoretical equations assume a completely constant height between the free surface and the outflow pipes.
This simulation replicates the environmental conditions in which the experiment was performed, along with the properties of the material used for the experiment, including the roughness of the pipes and many more. When running the simulation and solving the steady state, we found the pressure at P1 and P2 to be as follows. The pressure P1 is found to be 84.788 kilopascals, and the pressure P2 is found to be 85.359 kilopascals.